Welcome to Get Your FRQ On. This question is from 1998. It's question 2, and it is calculator active. In the question stem, we are given a function, f of x equals 2x times e to the 2x, and that's it. That is the question stem. In part A of the question, we are asked to find the limit as x approaches negative infinity of f of x and the limit as x approaches positive infinity of f of x. Starting with the limit as x approaches negative infinity of f of x, that limit is equal to the limit as x approaches negative infinity of 2x times e to the 2x, which is equal to the limit as x approaches positive infinity of negative 2x over e to the 2x. Now, it might not seem obvious why we want to get this into a fraction, but in order to do this, we're going to end up having to use L'Hopital's rule, and in order to use L'Hopital's rule, it needs to be written as a fraction, so that's why. All right, so the limit as x approaches infinity of negative 2x over e to the 2x, if I know I'm going to use L'Hopital's rule here, and it's pretty obvious in a few minutes why that is the case, we have the limit as x approaches infinity of negative 2x over the limit as x approaches infinity of e to the 2x, and that is of the form negative infinity over infinity, which is an indeterminate form. That's one of the indeterminate forms for which we would use L'Hopital's rule in order to find this limit. All right, so now we've established that the limit in question is an indeterminate form and that L'Hopital's rule is required. If a question like this were to actually show up in a free response question, you would have to show that the desired limit is in fact of an indeterminate form before you use L'Hopital's rule. All right, so that's why that step is included. It is of an indeterminate form. We've shown that. We're good to use L'Hopital's rule. All right, so the limit as x approaches negative infinity of f of x is the limit as x approaches positive infinity of negative 2x over e to the 2x, but if we apply L'Hopital's rule here, which we should, that limit is equal to the limit as x approaches infinity of negative 2 over 2e to the 2x, which is the same as the limit as x approaches infinity of negative 1 over e to the 2x, which is 0. All right, so the limit as x approaches negative infinity of f of x is 0. The limit as x approaches positive infinity of f of x is a little bit easier to handle. The limit as x approaches infinity of 2x e to the x is just infinity, and therefore that limit does not exist. In part B, we are asked to find the absolute minimum value of f and justify our conclusion. By inspection, f of x is differentiable and continuous on its entire domain, 2x times e to the 2x. There's no discontinuities. Nothing shows up as a result of it being a product. It's differentiable and it's continuous. Our function f of x, therefore, can have a minimum value either at an endpoint, but since we're talking about the entire domain, really is no endpoint. So we are looking specifically for some value of x for which the derivative of f is equal to 0. Okay? Well, in order to determine that, we actually have to find a rule for f prime. To do that, we'll use the product rule, 2x, or 2 times 2x e to the 2x, plus 2 times e to the 2x, simplifies to 2e to the 2x times 2x plus 1. And if we want that to equal 0, well, I have two factors. The product is 0, so each of the factors could be 0. But 2 times e to the 2x is never going to be 0. So the only hope this thing has of being 0 is specifically when 2x plus 1 is equal to 0, which would imply that x is equal to negative 1/2. Okay? Well, the function value at negative 1/2, f of negative 1/2, we can find simply by using our calculator. We don't even really need to do that. That's going to be 2 times negative 1/2 times e to the 2 times negative 1/2, which is just negative 1 times e to the minus 1, which is negative 1 over e. Okay? So that's the absolute minimum value of f. It's the only place it can occur since there are no endpoints here. All right? We don't have to check to see when 2e to the 2x will equal 0. It's never equal to 0. But we do have to verify that this is, in fact, a minimum value. All right, so the 2e to the 2x, that's always positive. All right, for all x, that factor is positive. So if f prime of x is to be negative, that would imply that the negative comes from the 2x plus 1, and so x would have to be less than negative 1/2. All right, so when x is less than negative 1/2, the function f is decreasing. Okay, but in order for f prime to be positive, all right, that would have to imply that x is greater than negative 1/2, which means that f is increasing after negative 1/2. So if f is decreasing before negative 1/2 and increasing after, f of negative 1/2 equals negative 1 over e is in fact an absolute minimum value of f of x. What is the range of f? Well, we just determined in part A that the limit as x approaches negative infinity of f of x is 0, and the limit as x approaches positive infinity of f of x is positive infinity. And we determined in part B that the absolute minimum value of this function is negative 1 over e. We also know, based on how this function is defined, that it's continuous and differentiable. So we're not skipping anything. There's no discontinuities that we have to account for. So our range here actually is y is greater than or equal to negative 1 over e. In part D, we are asked to show that any function of the form bx times e to the bx has the same absolute minimum value for all values of b. Okay, so we're going to go about this in pretty much the same way. Okay, fine, b is some number. Let g of x be this function bx e to the bx. Okay. We have to find its derivative. G prime of x is going to be b squared x e to the bx plus b times e to the bx. Okay. There's a common factor here of b times e to the bx, and if we factor that out, we get b times e to the bx times bx plus 1. Okay. But the same reasoning applies as in the previous steps. B times e to the bx is never going to be negative as long as b is positive. And if it is positive, that will just change up the solutions from the other factor. Those will now be the opposite sign as well. All right, so if I solve this for 0, right, g prime of x equals b times e to the bx times bx plus 1 equals 0 implies that bx plus 1 is equal to 0, which would be x equals negative 1 over b. All right, now this term, the b times e to the bx, could be negative, but it can't be 0 unless b is equal to 0, which I don't think we're allowing here. All right, so if I evaluate the function g at negative 1 over b, we get b times negative 1 over b times e to the b times negative 1 over b, and we get the same cancellation that occurred in the previous part of this problem. We get negative 1 e to the minus 1, and this is independent of b. All of the b's cancel in this work, and we still get negative 1 over e as the absolute minimum value of this function, no matter what the value of b may be. So for all non-zero b, the absolute minimum value of these functions of the form b to the x, or b times x e to the bx, is always going to be negative 1 over e.